Welcome back, Deep Divers. Today we're gonna be diving into something pretty electrifying. Literally,
Sounds exciting.
it is. We're talking about electricity, and we've got some really interesting source material for this one.
Oh, let's hear it.
So we've got some notes from a National 5 physics class,
Right.
and we also managed to snag the course specs from the Scottish Qualifications Authority.
Wow. Pulling out all the stops for this one.
You know it.
Oh.
So we're going to try to make sense of all that, break down some of the big ideas.
Sounds like a plan. Where do we start?
Well, I figured we could kick things off with the basics: voltage, current, resistance, the ABCs, electricity.
The fundamentals. Always a good place to start.
Right. So I was hoping you could maybe paint us a picture. What are these things, really, in a way that everyone can get?
All right, so let's imagine a water park. Yeah. With those big winding water slides.
Okay, I'm picturing it.
So think of voltage as the height of the slide. The taller the slide, the more potential energy you've got at the top.
Right. The bigger the drop, the more thrilling the ride.
Exactly. And in an electrical circuit, voltage, or what we call potential difference, it's that same idea. It's the energy given to the charges. It's what pushes them along.
Okay, so voltage is the oomph, the driving force behind the electricity.
Precisely. Now, let's talk about current. Think of that as the water flowing down the slide.
Okay, got it. The flow of electricity.
Right. And the more water flowing, the stronger the current. Lots of water, high current. A trickle, low current.
So like a rushing river versus a gentle stream.
Perfect analogy. Now, where does resistance fit in? Well, think of it like the friction between the water and the slide.
Okay, makes sense.
A smooth slide, the water flows easily, low resistance. But a rough slide, with all sorts of bumps and obstacles, that's going to slow down the water. That's high resistance.
So a rough slide is like a resistor in a circuit. It makes it harder for the current to flow.
You got it. And speaking of resistance, I remember that the student notes had a pretty striking real-world example. They talked about electrostatic discharge.
Oh, yeah. Like when you get a shock from touching a doorknob.
Exactly. But the notes actually focused on how that discharge can damage microchips.
Oh, wow. Really?
Yeah. Apparently, those chips have tiny pathways for current to flow.
Okay.
So when that static electricity discharges, it's like a sudden surge of electricity trying to cram through those tiny spaces.
Ouch. They can't be good.
It's not. The resistance is so high in those tiny pathways that it creates a lot of heat, and that can be enough to fry those delicate components.
So even a little bit of current can cause big problems if it hits high resistance.
Absolutely. It's a good reminder to be careful with static electricity around electronics. But you know what? This actually brings us to a really fundamental idea that ties all three concepts together.
Ooh. And that is Ohm's Law.
Okay, Ohm's Law. I've heard of it, but I'll admit I'm a little fuzzy on the details. Can you give us the rundown? Of course. Let's break it down. So Ohm's Law basically says that the current flowing through, say, a wire is directly proportional to the voltage across it,
Okay.
but inversely proportional to the resistance.
So more voltage, more current.
Exactly. Think of it like this. If you have a bigger battery, you're going to have more push, more voltage. That means more current will flow.
Makes sense.
And on the flip side, if you keep the voltage the same, but you increase the resistance,
Like using a thinner wire.
right, or a longer wire, that'll make it harder for the current to flow. So the current will decrease.
Okay, so it's all about that balance between voltage, current, and resistance.
You got it. And you know what's really cool is that our student notes, they actually have a little experiment you can do to see Ohm's Law in action.
An experiment. I love a good experiment. What do we need?
Well, you'll need a power supply, but not just any power supply, one with variable voltage. That way you can adjust the push, the voltage.
Okay, a variable voltage power supply.
Then you'll need a resistor, to introduce some resistance into the circuit.
Resistor, got it. What else?
You'll need an ammeter. That's to measure the current flowing through the circuit.
Ammeter.
And a
Yeah.
voltmeter. That'll measure the voltage across the resistor.
Ammeter voltmeter. Starting to sound like a real lab here.
Almost. Don't forget the connecting wires, to hook everything up. And of course, a switch to control the flow of current.
Okay, switch. Got it. So how do we put all of this together?
All right, so first, you got to connect the ammeter in series with the resistor,
In series, meaning?
meaning the current flows through both of them in a single path.
Oh, okay.
Then you connect the voltmeter in parallel with the resistor.
Okay,
That way it can measure the voltage difference across the resistor.
got it.
Once you've got it all wired up, you close the switch and let the current flow.
Time for the magic to happen. Then what?
Well, then comes the fun part, taking measurements. You start with a low voltage on the power supply, and you write down both the voltage reading from the voltmeter and the current reading from the ammeter.
Okay.
Then you just increase the voltage a little bit, take another reading, increase it again, another reading, and so on.
So we're basically building a table of voltage and current readings. What do we do with all that data?
We turn it into a beautiful graph. Plot the voltage on the axis and the current on the x-axis.
Ooh, a visual representation. I like it.
Right. And if you've done everything right, you should see a straight line that goes right through the origin.
And that tells us?
That tells us Ohm's law is at work. The straight line means the current and voltage are directly proportional, just like the law says.
Okay, that makes sense.
And there's more. The slope of that line, you know how steep it is, that actually tells you the resistance of the resistor.
Hold on, we can figure out the resistance just by looking at the graphs.
Exactly. Remember that the equation for a straight line is y equals mx plus c.
Yeah, vaguely. It's coming back to me now.
Well, in this case, y is the voltage, x is the current, and c, the y-intercept, is 0 because our line goes through the origin.
So it's just y equals mx.
Yep. Which, if you think about it, looks a lot like Ohm's law. V equals IR. That means M, the slope of the line, is the same as R, the resistance.
Wow. So a steeper line, higher resistance.
You got it. Pretty neat, huh?
Super neat. But I gotta ask, is it always that simple in the real world? Are there things that could mess up our experiment or make Ohm's law not work perfectly?
You bring up a good point. Things are always a bit messier outside the lab.
Right.
One thing that comes to mind, and the source material actually mentions this, is temperature.
Ah, temperature. How does that play into all of this?
Well, the resistance of a conductor like our wire, it can actually change with temperature.
So if our resistor got hot during the experiment, that could throw things off.
Exactly. Most of the time, as the temperature goes up, so does the resistance.
Why is that?
Think about those electrons flowing through the wire. As the wire heats up, the atoms inside start vibrating more and more.
Making it harder for the electrons to get through.
Exactly. It's like trying to walk through a crowded room. The more people are moving around, bumping into each other, the harder it is to get through.
Great analogy.
So, our simple experiment, it's a good starting point, but it's important to remember that in the real world, things can get more complex.
Right. Real-world engineering, I imagine, it has to take all sorts of factors into account.
Absolutely. Temperature, type of material, all sorts of things. But you know what? Even with all that complexity, it's still pretty amazing that this simple law, Ohm's law, holds up so well.
It's a fundamental building block.
Exactly. And speaking of building blocks, I think you mentioned wanting to try this experiment yourself.
I am. I'm getting all inspired now. Can we do a quick recap of what I'd need to get started?
Sure thing. First things first, you'll need that power supply, remember, with the adjustable voltage.
Got it. Variable voltage power supply.
And you'll need a resistor. Or, hey, even better, grab a few resistors with different resistance values. That way, you can see how changing the resistance affects the current.
Okay, power supply, resistors. Check and check. What else?
You'll need your trusty ammeter and voltmeter, of course, to measure the current and voltage, respectively.
Right. Those were key for taking those readings. Ammeter, voltmeter. Check. Anything else?
Don't forget connecting wires to, well, connect everything. And that switch so you can control the current flow.
Okay, connecting wires, switch. I think I'm all set. Thanks for the walkthrough. I can't wait to set up my own little electricity lab.
Have fun with it. It's always a thrill to see those scientific principles come to life.
Speaking of thrills, let's talk about different types of current.
Oh, you mean AC and DC?
Yeah. Our sources mentioned those briefly, but I'm curious to learn more. Can you break down what they are and how they differ?
Absolutely. Let's go back to our water park analogy just for a moment. Picture two types of water slides.
Okay.
One slide has a constant, steady flow of water, like a continuous stream that's like direct current, or DC.
Okay, so a steady stream of electrons.
Exactly. Now imagine the other slide has water surging back and forth, almost like waves in a pool.
Okay, I can picture that.
That's like alternating current, or AC.
So DC is a constant flow, and AC is this back and forth flow. Fascinating. What makes them good for different things?
Well, DC is really good for applications where you need that steady one-directional flow, like in batteries, for example.
Yeah.
Or electronic devices.
Makes sense. What about AC?
AC is actually more efficient when you're transmitting electricity over long distances.
Really? Is that because of resistance?
You're on the right track. Resistance is a factor, but the real key with AC is that it can be transformed.
Transformed. What do you mean?
We can easily bump up the voltage for transmission and then bring it back down to a safe level for use in our homes.
Ah, so we can send high voltage over long distances without losing too much energy to resistance, and then step it down to a level that's safe to use.
Exactly. It's a pretty ingenious system.
It is. But how can we actually see these different types of current? I think our sources mentioned something called an oscilloscope, right?
Ah, yes. The oscilloscope. It's like a magical window into the world of electrical signals.
Okay, color me intrigued. What does it do?
It basically lets us see the voltage of an electrical signal as it changes over time, like a graph on a screen, but instead of just dots, it's a live feed of the signal.
Wow. So we can actually see those waves of current in action.
Exactly. And that's how we can tell the difference between AC and DC. With DC, you'll see a flat line on the oscilloscope because the voltage is constant. But with AC, you get this beautiful wave pattern going up and down.
That's so cool, seeing the invisible made visible. I love it.
It really is remarkable.
Well, I gotta say, this deep dive has been electrifying, to say the least. We've learned about voltage, current, and resistance. We've demystified Ohm's law, and we've even gotten a glimpse into the world of AC and DC.
And we did it all through a handful of student notes and a course specification.
Proof that you can find fascinating knowledge in the most unexpected places.
It really shows you that sometimes the simplest explanations, the most basic examples, those are the ones that really stick with you.
Absolutely. And that's what we're all about here on the deep dive, right?
Yeah.
Taking those sources, whatever they may be, and digging out those little gems of knowledge.
Exactly. It's like panning for gold. But instead of nuggets, we're after insights.
Love that analogy. It's funny because while we've been talking about these electrical concepts, voltage and current and all that, our sources actually touch on something pretty amazing.
Oh, what's that?
They mention using solar cells with adjustable areas to power spacecraft.
Wow. For long missions, I'm guessing?
Yeah, those deep space journeys. It's incredible to think about, right? Harnessing the power of the sun, converting it to electricity,
Yeah.
and using that to travel through space.
It really shows you how far-reaching these basic principles are.
Right. We're talking about space exploration here, and it all comes back to voltage, current, resistance.
It's mind-blowing when you think about it. These aren't just abstract ideas. They're the foundation for technologies that are pushing the boundaries of what's possible.
It really makes you wonder, what else can we achieve? What other incredible technologies are out there, just waiting for us to unlock them?
The possibilities are endless. As long as we keep exploring, keep learning, who knows what we'll discover.
Well said. Well, on that note of endless possibilities, I think it's time to wrap up our electrifying deep dive into the world of electricity.
I think so too. We've covered a lot of ground today.
We have, from those fundamental definitions of voltage, current, and resistance, all the way to the elegance of Ohm's law, and even a peek into the differences between AC and DC.
Hopefully our listeners have a new appreciation for the power of electricity and the amazing ways we've learned to use it.
Absolutely. And as you go about your day, flipping those light switches, plugging in those devices, take a moment to think about all those tiny electrons buzzing around, making it all happen.
It's a pretty amazing world when you stop to think about it.
It is. Until next time, deep divers, stay curious and keep those brains sparking.